Okay, yes. So welcome to the second oral session from CRV. It's my pleasure to host Adriana and Kate today. Ariana Romero from Facebook AI will give her the first presentation. Adriana is is a research scientist at Facebook AI. She's also an adjunct professor at McGill University. So as we just discussed, the best of two worlds. You get to work with students, you can do your research, and you get paid for it. She was a postdoc at Mila before that with Yusha Benjua, and she has a PhD from the University of Barcelona. So quite a lot of experience here, and I'm really curious what she will share with us. Her research is generally on developing models and algorithms that are able to learn from multimodal and real-world data. She has also some active reconstruction in there. I think that's something I'm super excited about. I had to work on that as well. It was super difficult. We didn't really get to do what we wanted to do, so I'm curious what she has to tell us. So yeah, with that, Adriana, please take the stage. Now it's coming up. Yeah, I think it was Kay interrupting you. Okay.
Is that all right?
So I'm really interested hearing about what you have to tell us, and yeah, take it away.
Yeah. So thanks a lot for the introduction, and thanks for inviting me to give this talk. I'm very happy to be here with all of you. So yeah, I guess I changed the title of the presentation, but the topic is going to be roughly the same. So I'm going to be talking about seeing the unseen, and more particularly about inferring unobserved information from limited sensory data. So let me start with a quick introduction. So as humans, we never fully observe the world around us, and yet we're able to build remarkably useful models of it. Let's see a very simple example of that. So here's a partial observation, and we know that this partial observation corresponds to a digit. And there are many ways in which we can fill in this partial observation such that we obtain a fully observed digit. For example, some of you might fill in this observation in such a way that it becomes a 7. Some others might fill in this observation in such a way that it becomes a 1 or even a 4. And so in order to improve the models that we build of the world, we reduce the uncertainties by acquiring new information, new observations, which potentially complement the previous information that we already had. So we improve our understanding of the outer space by acquiring new observations, or similarly, we gather information from the underwater by taking deep dives. And we also improve our understanding of our own inner space or the inner space of other organisms on Earth by exploring new acquired observations. And by studying this newly acquired information, we are able to increase our knowledge and are able to build better models of what once was invisible to us. And so if we go back to our simple example from the beginning, if we collect additional information, say that we have this example and I give you this additional information, this additional stroke in the partial observation, then the number of possible ways in which we can complete this partial information, this partial observation reduces. And in this case, I guess we could all agree that the most likely completion would be the digit number 7. And so we keep improving our models of the seen and the unseen by acquiring and leveraging information that complements the information that we previously had. And machine learning systems are often required to infer unobserved information from the observed one that is operating in a similar setup than the one that I have described. And we will see one particular example of that. So let's start with the example. So if I show you this image on the left of the slide, you see that there is an object that is handheld. And the question would be, given this single view image of the object, can we infer the shape of the object? So the full shape of this object, the full 3D shape of the object. So this is the problem of 3D shape reconstruction, which has been tackled in most cases by the computer vision community from either a single view or multiple view images. And in this work, we will focus on the single view formulation. So the goal here will be to infer the 3D shape of an object from a single view image of this object. And again, you have this problem that there might be many ways of filling in this missing information. And this number of ways in which one might fill in the information of the 3D shape might be more or less difficult depending on the view of the object that we have. So in order to limit the possible ways in which one could fill in this missing information, and in order to recover better 3D object shapes, we explored how to leverage the complementary information between vision and touch modalities. So one may ask, why vision and touch? So first, we believe that the haptic information is relatively underexplored as a modality, especially when combined with vision. And gaining understanding on how to best represent and leverage this modality can enable potentially more interesting questions around object manipulation. Moreover, vision and touch provide complementary information, and I'm going to try to convince you of that. So although we only have a single view image of the object that we want to reconstruct, vision provides a very strong global context for the object in view. It gives us a good idea of the general shape of the object and the rough position of the object in space. However, vision also has its limitations, its ambiguities, which might hinder the quality of the reconstructed objects. For example, vision suffers from occlusions and from bas relief. At the same time, we have tactile signals, which provide highly detailed information about the local structure of the object being touched. The tactile signals also provide us important positional information, since we know that the object being touched will be within the reference frame of the hand. However, touch information is also limited somehow, in that the local information that it provides will very often fail to extrapolate well into global shape understanding of the object, even when having access to strong object priors. So therefore, I hopefully convinced you at this point that vision and touch provide complementary information, more particularly complementary global and local information about an object. So in order to explore the complementarity between the visual and the tactile signals, we started by building a visual tactile dataset of object grasp interactions. So I won't go into too much details about how the dataset looked like, but just to give you an overview, we simulated object grasp interaction using an Allegro hand, which is equipped with high resolution vision-based sensors at each of its fingertips. We also used objects from publicly available 3D computer vision benchmarks, given their ubiquitous use in research. And we performed this object and hand interaction in simulation. And this resulted into an image of the interaction, which you see on the slide, and also 4 tactile signals depicted on the slide as well. Once we had the simulated data set constructed, we designed an approach to fuse visual and tactile signals for 3D shape reconstruction, the problem that we were initially interested in. So we operate in the mesh space, and we start by representing an object as a collection of disjoint mesh surface elements, which are called charts. Some of these charts are reserved for tactile signals, and some of these charts are reserved for visual signals. So the first step is to predict the touch charts from our touch recordings from our dataset, and we do that via a unit-like model. So we get 1 chart per fingertip. We then initialize the vision charts as a sphere and project the visual signals coming from the input image onto all charts. That way we have some features coming from the input image at each one of the vertices of these charts. And then we feed all the charts, the visual and the touch charts, into an iterative deformation process, which leverages recent advances in graph neural networks and where we enforce touch consistency. That is that at the end of this deformation process, the touch charts are copy-pasted back to their original position in such a way that we fill in the missing information of the 3D shape by leveraging the visual signals. As a result of this process, we gain a global prediction of the deformed charts. We get an object prediction, and the whole system is trained to minimize the chamfer distance. So moving on to some results of this pipeline. The first experiment that we performed aimed to highlight the benefits of leveraging both modalities, vision and touch, in the context of 3D shape reconstruction. Therefore, we compare how different modalities do on their own and how both modalities perform together. So here results are in terms of chamfer distance, so the lower the better. And as expected, when compared to vision modality, touch alone performs very poorly. At the same time, vision-only signals achieve pretty good results already. And however, we see that when we combine both vision and tactile signals in both setups that we're considering, we consistently perform better. We designed a second experiment in which we examined the effect of providing increasing number of grasps. So the only practical change here in terms of the method is that instead of having 4 charts corresponding to the touch signals, we will increase by 4 the number of touch charts every time we add an additional grasp. So we plot here the percentage improvement in chamfer distance with respect to using a single grasp. And the blue line shows the improvement when only using tactile information, and the orange line represents the improvement when using both visual and tactile signals. What we observe is that by increasing the number of grasps that we provide random grasps here, the reconstruction accuracy improves on both settings. So let's briefly look at some qualitative results. So what I'm showing here on the left column is the input vision signal. And then from left to right, we have the reconstruction using no vision with a single grasp. Then we add vision with a single grasp, and we keep adding the number of grasps coupled with vision. The first row is the object reconstruction. The second row depicts the error around the surface of the object. So what does this tell us? So in the first case where we do not use any vision and we have a single grasp, we see that the reconstruction doesn't have very high quality. As soon as we leverage the visual signal, we see that the error is mostly concentrated at the top of the bottle. And as we keep adding additional grasps, the error is further reduced. So we visually confirm that the model gains additional insights into the nature of the object being touched by touching new areas on the object surface. And in light of the previous results, where we showed that adding random grasp, we were able to improve the reconstruction quality of the objects, we more recently explored how to learn touch exploration policies in order to improve upon our previous results. In particular, we posed the problem as a sequential decision-making problem where we want to decide where to touch next, and trained DDQN agents, so reinforcement learning-based approach, to decide where to touch the object next in order to minimize the object reconstruction error. So I'm going to show a couple of videos here of how these policies perform. So you will see on the left a policy that only leverages tactile signals, so no vision, and on the right a policy that leverages both vision and touch signals, but the policy is always touch exploration. It's just that we leverage visual priors. And you will see some dots appearing around the object surface, so that corresponds to the grasp, and you will see with how the object reconstruction evolves with each additional grasp. So let me play those for you. All right. Oh, there is only one playing. Second one as well. Okay, great. So what we see here is that with every additional touch added, the reconstruction improves. And there is also a significant difference between what we see on the left and what we see on the right, meaning that when leveraging vision, we see that we are able to obtain reconstructions that are a lot smoother. And I'll be wrapping up this talk because we're running out of time already.
You're good in time. You're good in time. No rush.
Okay. Okay. So in this talk, what we have discussed is the problem of seeing the unseen. And that is the one of inferring unobserved information from the observed one. And we took the example of 3D shape reconstruction from a single view image. We saw how we could leverage visual information to complement the tactile information in order to improve 3D reconstruction systems. In particular, we introduced a simulated data set of grasp interactions between a robot hand and a 3D shape. We proposed a chart-based approach to 3D shape reconstruction, which was suited to leverage both modalities, so the tactile and the vision modality. We demonstrated that this approach benefits from both modalities, so the tactile signals and the visual signals, and improves the results upon both single modality-based approaches. We showed that by increasing the number of randomly selected grasps and hence increasing the tactile information that we provide the model with, we could improve our results. And finally, we addressed the problem of active acquisition of touch signals and learned shape exploration policies, which in practice outperform our previous results. So I'll close the presentation here and
awesome.
take any
Thanks
questions.
a lot, Adriana. Great presentation. And yeah, we started 5 minutes late a bit because the AI keynote, people were coming over a bit because my intro took so long. So don't feel stressed as a speaker. We had a 5-minute delay, but we have a buffer here and there. So don't worry about this. Yes, so we do have time for questions as well. If you want to ask your question in person, then simply raise your hand. If you prefer to chat and I can read it out, just type your question in chat. I will start with one, so you have time to type. I had a couple of ones actually. So first of all, I wondered if you see this maybe big goal of AI, whether we want to build this agent which learns by itself. Do you think it's maybe easier to learn from touch? So I don't know, we humans as a baby, probably we touch at a lot of things, and maybe our vision is even not that developed at first. Is it somewhat easier to work with this touch modality, and we should do more of that?
That's a good question. I guess I do not have like a definitive answer for that. So I agree with the sentiment that the touch modality is perhaps underexplored, and it's something that as humans we use a lot. What we see in practice though is that because touch is very, very local, it becomes very difficult. If you think of starting a pipeline with touch only and eventually then leveraging vision because it becomes better as we develop as babies, or like because you start in a dark room and suddenly the lights are switched on and so on. So I think there is still a lot of exploration to be done with the tactile modality, but I also believe that if we think from the perspective of learning, probably it's a good idea to leverage as many modalities as we have access to.
Yeah, it seems to be a very unique one, which I haven't really thought. You get this, point measures, very accurate, but then you don't get the broader structure. There's a quick question from Zuman. Do you mind sharing the computational resources required for such tasks?
That's a good question. So I cannot give you exact numbers. Definitely training RL agent is costly. Running the simulator requires quite a bit of CPU, but the models that we are building are themselves not that big. And most of the models that we developed, like being the reconstruction model or the reconstruction with the policy models, most often fit in 2 to 4 GPUs.
Okay, that's doable. Any follow-up? Let me see, no hands up yet. I have one more question then. And there was about how you address the problem. You had lots of learning components. You didn't have the time to go into detail, but you seem to have some reinforcement learning there. And how much do you still plug in some of geometric priors or domain knowledge that you want to reconstruct the surface, and where do you see the sweet spot there?
Mm-hmm. So that's also a good question. So I didn't have the time to go into details into the models that we build. I think like in the reconstruction part, the key component that we found to be helpful is this idea that I briefly mentioned of copy pasting the tactile information. The reason for that is that although we start from touch recordings, which are essentially images, it's very easy in a sense that the predictions are very accurate. So we can rely on these very local tactile reconstructions a lot. And so this is the reason why we pushed in this idea of kind of fixing those and trying to fill in the missing information with with the visual signals. That said, we didn't necessarily handcraft any additional inductive biases into the model. As for the
There's a good question from Calden about assuming rigid objects. That's probably some assumption you make.
Yeah, all of yes, no, that's a good point. So all of the objects that we've dealt with up to now are rigid objects.
So squishy things come next.
Hopefully.
Okay, great. If you have further questions, then please post them in chat, and I think Adriana could answer them in chat as well. So thanks again, Adriana. Great talk, amazing research. I invite everyone, I will do certainly, to look more into her research papers as well. Check out her web page. Next up is Kay. Are you ready to give your presentation? So while he's setting up your screen, let me introduce you. So Kay Lee is an assistant professor at Simon Fraser, so just next door, and actually where this conference is supposed to happen. He was previously a member of the Institute of Advanced Study, and she received the PhD from Berkeley and the bachelor from Toronto, so quite connected to Canada, as nearly all of our speakers are. And yeah, Kay is interested in a broad range of things: machine learning, computer vision, NLP, and generative modeling, nearest neighbor search, and also really basic things like learning to optimize. I'm really curious what he's going to tell us today. The title is Worry-Free Image Synthesis Without Mode Collapse. I could really need worry-free these days. So take the stage and tell us more about it.
All right. Thank you so much for the introduction. First of all, can everybody see my slides?
Yeah, we see the slides, and your sound is very good.
It's awesome. Good. Okay. So this talk, I'm going to be talking about image synthesis, right? So first, let me introduce what that is. So image synthesis just refers to the problem of generating high-resolution images with complex structure from some inputs. So we have some examples here. So we can, for example, be trying to generate an image from a layout of the scene, right? A segmentation map in this case. Or we could be trying to colorize the image, right? So we are given a grayscale image, and then we're trying to generate color image, or the input could be just this low-res image, right? In which case, we're just trying to generate a high-res image. So existing methods are mostly based on conditional GANs, right? So let me talk about how they work. Conditional GANs essentially take in two things as inputs. One is the image that we're conditioning on, right? So in this case, it could be the segmentation map. Is also going to take in a noise as inputs. And so both of these things are going to go into the generator, and the image that we get out, right, is what we want. So the conditional GAN is going to essentially take this input and then train a discriminator and say, is this real or not, right? And the goal of the generator is to try to make this seem as real as possible. So ideally, what we want to happen is, after training, we want to vary the noise. So if we feed in a different noise vector, right, like this, we want to get a different image. For different noise vectors, they should really map to different images. However, this doesn't actually happen in practice. So it turns out that after training, oftentimes you feed in different noise vectors and the resulting image doesn't change, right? So you just get a single image out for a given input. So, and that is known as mode collapse, and it's basically ignoring this noise vector that's being fed in. So essentially, if you think about it in terms of probability distributions, what's happening is that if we have a true distribution that is multimodal, right? So this is the true distribution, that's this red curve here. This is the probability density. So you actually are supposed to have different images for the different peaks, right, in this density. So, you can have like these things. But for the model that you are actually learning, so that's this model distribution, which is the gold curve, it's only picking out one particular mode. And so it's only modeling one of these images, it's just ignoring all the other possibilities. And so usually what you get is if your real data actually has a lot of different modes, right? So these are like different clusters, for example. In this case, the animation is not playing very well, but essentially at the end, you're only assigning good density, right, to this part of the data, right, and ignoring this part.
We could see the animation initially, but now your screen is somehow black.
Oh, really?
Oh, now it's coming back. I don't know. It's back now.
Okay. That's weird. Okay.
And we could see the animation, so I think that was clear. It was just for a few seconds black for some reason.
Okay, I see. Okay, thanks. Yeah, let me know if there are any technical issues.
All good. Your voice is still clear.
Great. Okay.
And
thanks.
image is back.
Awesome. Okay. Now let's hope that this works. I'm supposed to be advancing to the next slide, but why is it? Okay. Okay, there we go. So why does mode collapse actually happen? Essentially, we're going to consider this simple two-dimensional example here. So the red data points are the real data points. The blue ones are the generated samples. And so when we are actually training the GAN, we're essentially keeping these red data points fixed and moving around the blue points, right? So these are the samples that we're learning to generate. Right, so red is real, blue is fake. So I want you to pay attention to how the blue circles actually move, right? That's what's going to happen when we train the model. So initially, when we actually train the discriminator, we're going to be essentially separating the red points from the blue points, right? So this boundary between the white and the yellow regions is the decision boundary. And so the yellow regions are the regions where the classifier thinks things are real, right? So the white regions are where it thinks things are fake. So when we then train the generator, we're going to be essentially pushing all these blue points towards the yellow regions. So that's what happens after sort of we've trained the generator, right, to convergence. And so then because it's perfect, right, discriminator is classifying things perfectly, we actually need to retrain the discriminator, right, to get a new decision boundary. And that's what we have now, right, again, separating the blue points from the red points. And so then we're going to push again, right? Push the blue points again when we train the generator. So you can see, there are these red points up here that are actually not covered by the generated samples, right? So it's sort of learning these points very well, but there's no blue point nearby, right, for any of these red points. So these are essentially the modes are being dropped by our generator. So what actually went wrong here? Essentially, if you think back to what happens, every generated sample is pushed towards the nearest data points. This makes sure that for every generated sample, right, we have a nearby data point, but it does not ensure the opposite, right? So it does not ensure that for every data point, we actually have a nearby generated sample. And so that's why modes are being dropped, right? So this directionality is key here, right? So you actually want every data point to be covered. So how can we actually fix this? It's actually simple. If you think about it, we can just swap the direction in which the data and the samples are being matched. So we will actually want every data point to be pulling the nearest sample towards it. And that's basically how our method works. And the method is known as implicit maximum likelihood estimation. Okay, so let's take a look at how that works using the same diagram as before. So again, just to remind you guys, the red points are the real data points, the blue points are the fake samples. And so what we do is for every real data point, every red points, we're going to look around and find the closest sample, right, to each one of them. So for example, for this one, right, that's the closest one, right? Same thing for these ones. And so we're going to do this for all the different red data points. I'm just showing 3 here for clarity. And then we're going to then pull the samples right towards the data points. So after we found the closest points, right, we're going to change the parameters of the generator, right, such that these things, right, become closer to the red data points. So we're going to do that for all the data points, of course. And so that is it, right? So here's what happens, right, when we actually run this algorithm. So on the left side here is, again, on the right-hand side is IMLE, right, implicit maximum likelihood estimation. You can see that, essentially all the different clusters are covered, right, by good probability density, right? Whereas for the GAN, you have very low probability density up here. Okay, now let's hope the next slide works. Every time I show a video, it's really slow when I try to mess the slide. Okay,
It
there
comes
we go.
okay through. So.
Oh, really? Okay, great. Okay. Okay, so here's the actual objective, right, that we use. So I'm not gonna bother you guys with the details, but essentially the important thing to note here is that there's no adversarial, optimization here, right? So it's a min and a min, right? So there's no minimax. And so that means we don't actually have to worry about the optimization diverging, right? So if we have a GAN objective, a minimax objective, right? What could actually happen is it never actually gets to where we want to be, right? Which this is the minimax solution, but it never actually gets there, right? So it keeps going around in circles. In this case, because it's a pure minimization problem, we can just train this using stochastic gradient descents, and that is known to converge, right, to a local optimum. So this is sort of an illustration of that. So this is plotting essentially the loss that we attain as we train the model. So you can see that the loss is going down always, and the quality of the generated image is getting better and better as we train for longer. Okay, so let me show you guys some empirical results. So we have a few different tasks here. So one is hyper resolution. So that's just what we call 16 times super resolution. So we're gonna be essentially expanding the width and height by a factor of 16. So this is the inputs. And now after we upsample it by a factor of 16, this is what we get out, right? So you can see a few things, right? One is, it's a good looking image. The other that's more important is that if we actually take a look at the different samples, right, as we vary the noise that's fed into the generator, they actually do give different results, right? So you can see that, the dots are varying, right? And they all look plausible, right? And they're all consistent with the input image. All right, now, so here are some comparisons with the GAN-based methods. So achieving better quality, and it's also, unlike the GAN, it's able to give you different samples, right, whereas the GAN is staying the same. And some other images. Okay, and now let's take a look at another task, right? So this is trying to colorize an image, right? So if we're given a grayscale image, right, we're trying to generate a color image from that. So we can try to, again, right, do the same thing, right? Try to generate different samples, right, for the same image, right? So you can see that it's varying this background, right? So, going from brown to green to blue, right? Also varying the color scheme a little bit, right, on the parrot itself. We can also try to do decompression. So what this is if you were to only given a JPEG compressed image, for example, right, that's pretty badly compressed. You see the compression artifacts here, and what we want to get out is an image, right, the original image. So this is the GAN-based baseline, right? This is our method. So you can see that it's giving you, something that's pretty close, right, to the original image. And also it's giving you different possibilities, right? So you can see the colors varying because the compression artifacts actually, sometimes they're green, sometimes they're orange, right? So you can't actually tell, right, whether it's actually coming from a green image or orange image. Okay, so some other examples here, right, for another image. And we can also try to generate an image from a segmentation mask. So this is, a scene, right, with cars and roads, right? So we can try to generate an image from this. So every pixel here is a label, right? So we know this is a car and that's a road, for example. And so we generate the different images, and then so you can see the skies are changing, right? And sometimes it's daytime, sometimes it's nighttime, right? And that is just because in this input, right, you don't actually know whether it's daytime or nighttime, and it can generate the different possibilities. Finally, we have something related. It's not really image synthesis, but it's trying to generate 3D shapes. So you can give it a partial shape of the input, and then it's going to generate like these different chairs, right? So this is the upper portion of the chair, and it generates like the different kinds of legs, right, that the chair could have. And so and that will be useful, right, in many contexts if you can only observe a part of the chair. Okay, and finally, just some quantitative results for in terms of comparison to GANs and VAEs. So this is a figure that shows you the precision and recall that's achieved by IMLE compared to GANs and VAEs for different models. So every dot actually corresponds to one model. So there are 800 different models here for 800 different GANs and VAEs for different hyperparameters. So this one, the start here is our method, right? So it's beating all these GANs and VAEs on both precision and recall and on different data sets. So this is MNIST and that is CIFAR. And that is it. So, more details, you can check out these papers and happy to take your questions.
Awesome. Leave your slide on so we can
Sure.
have a glimpse of them. Thanks a lot. Yeah, really, we had 2 mini keynotes. Amazing work. Any questions? Raise your hand. I will fill in until then. Seeing both talks one after another, it seems somewhat related perhaps to the chamfer distance we saw from Adriana. She was minimizing, I guess, the distance between 2 surfaces. Is it somewhat related to what you are doing here?
Yeah, that's a good question. So you can think of chamfer distance. So chamfer distance is usually defined in terms of surfaces, right? So the surface here would be actually the manifold that's given to you by the generator. So the one distinction is just the direction in which you do the matching, right? I mean, depending on the analogy, basically, right? So which is the surface and which is the points, right? You can either do the matching by pulling the closest sample right to each data point, or the other way around, right? Pulling the closest data point to the sample, right? So depending on which way you do it, right? So one direction is going to give you more collapse, the other direction is going to give you this. So you just have to make the right analogy. But yes, it is related. Yes.
Yeah, I haven't dealt. I think we shouldn't jump into all the details. Any other questions? I wanted a bit from the general picture. You were drawing these beautiful maps of what's going on in the latent space. First of all, I wondered how realistic are these? Like, is this really what's happening? Or is there some phenomena which you essentially can't explain with the mental model which you observed, either using GANs or your implicit MLE approach?
Yeah, right. Yeah, so I mean, so certainly in the 2-dimensional case, right? So we show a 2-dimensional case. That is what is happening in a higher dimensional setting. I mean, it's just the picture becomes a whole lot harder to draw, right? But so you get a decision boundary that's not, that's not very complex geometrically, but it's just spans over a much higher dimensional space. But intuition still holds, right? It is still the case that in the case of the GAN, the samples are are being moved right closer towards the data manifold, right? So you can imagine that there are just some portions of the manifold that doesn't just attract any the samples, right? And that will be giving you more collapse. But it is a more nuanced picture, right? Because the decision boundary actually looks different. And so this is.
Should we use your implicit MLE? Should we use it for any task where we currently use a GAN, or is there some drawback?
Right. Yeah. So I mean, so one thing is certainly for IMLE, right? We need to use a bigger architecture than the GAN because the GAN can just sort of ignore a large chunk of the training data, essentially, right? And then so it's learning to fit the data that it does fit very, very well, right? But in our case, because it's actually trying to fit all the data, right? Naturally, you need to have a higher capacity model. Now you can argue that in some cases, if we only care about a subset of the data, right, then you actually want to have a smaller model. That will be one scenario, though you could actually extend this approach to be saying, I only actually want to do the matching for the top 10%. So that is possible. But at least in the way that it is currently, then the GAN can essentially the capacity to collapse modes is actually doing wonders in terms of the amount of model.
So I have struggled so much with GANs.
Right.
Really, we should try this out. I'm happy to sacrifice the GPU and capacity on this. Okay, thanks again, Kay. If I